Okay, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207, Calculus 2. Let's actually jump in. Let me share my screen here. Okay, and there we go. So hopefully you're all seeing that. Let me make sure I can see the chat in the other screen. Okay, so, all right, I think we're good. So, as you can see on the screen, we are going to be doing partial fractions today. Make that a little bit. We're going to be doing partial fractions today. That being said, there are a couple things I wanted to mention prior to this. So, as you guys may have heard just now, some people were having trouble. It seems like they weren't getting the unlimited attempts on the homework. I refreshed the settings like 15, 20 minutes ago at this point, and I know someone who was having trouble before said that they're not having trouble now. So I would assume that everyone is okay with that at the moment. So after class, you can double check in with the homework again to see if you have unlimited attempts enabled, and you can let me know if that worked. Seemed to work for someone. Another thing, I suppose, just before we get started, is actually in relation to another problem that I wanted to talk about. It's related to the last topic, to trig substitution, but it actually will provide a nice segue in today's topic. So I created an extra tab here on a Q&A. So I met with several students this week in office hours, and I got asked a variety of questions. However, there was one question that kept coming up where literally everyone I met with in office hours asked me about this question. So I figured that it is of general interest to actually look at this problem. So it was a problem of this form that you see right there. It looked like the square root of something squared plus x squared all over x dx. The a value was different for everybody. To make it look nice, I'll probably just do this with a equals 1 so you can see it. But this was an issue that a lot of students had. Pretty much everyone I met with in office hours over this past week brought up this WebAssign problem. So I thought I would talk about it because on the one hand, we do know enough to do this problem if we remember about our inverse hyperbolic trig functions. But it seems that WebAssign didn't like that, and I'll talk about that in a little bit. But on the other hand, the way to finish this up without the use of such functions would be to use the thing that I'm going to teach you guys about today. So I figured it would be a nice thing to actually bridge the gap between the last topic and today's topic. So I want to talk about this for a little bit. So we are going to look at a problem like this, the integral of a squared plus x squared all over x dx, where a can, of course, be any constant, right? Or any non-zero constant. So let's just say, for the sake of argument, for simplicity, let a equals 1. So let's look at this problem. So we have the square root of 1 plus x squared all over x. Now at this point, we only know about, the thing that we know that would tackle this is trig substitution. Let's actually do that. So there are several ways to attack this. One way is to do a trig sub. It was in the section on trig sub after all. What would be the correct trig sub here if you wanted to do this with trig sub?
Tan theta, sorry.
Right, x equals tan theta. So you go in, your dx here will be secant squared theta d theta. And so your integral would look like, well, 1 plus x squared would be 1 plus tan squared, which would be secant squared. Then you take the radical of that, so you only end up with a secant. The x is, of course, tan theta, so there's a tangent. And your dx would become the secant squared theta d theta. Okay. Now, you could actually go up several different ways at this point as well. I know some people switched everything to sines and cosines because they can see things, they can see little tricks nicer when they do that, which is completely fine. Not completely necessary though. One way that you could do this is to multiply and divide by tangent. So I multiplied the top and bottom by tangent. What you realize then is that the denominator here is actually secant squared theta minus 1. And what I would do now, because I have this whole tangent theta secant theta here, it makes a substitution of secant theta viable. So I would go in and I can do a substitution u equals secant. Your du would be secant theta tan theta. And so now this integral would become the following: u squared over u squared minus 1. Okay, so you can start out with a trig sub, x equals tangent theta. Eventually, you'll get to this integral. Now, this integral is a very interesting integral because on one hand, you'll need something esoteric like an inverse hyperbolic trig function to deal with it. The nicest way you could deal with it at this point with what you currently know, with what I currently told you, would be that. So you would do something like the following. You would subtract 1 and add 1. Why would I do that? So that I can split this guy into 1 plus 1 over u squared minus 1. And then recall that there was a rule that the integral of 1 over 1 minus x squared was actually the inverse tanh. And so I can actually integrate this as u, and integral of 1 is going to be u, and the integral of that guy is actually going to be the negative tanh inverse. Of course, your u is secant. And then you can do the trig back substitution. Not going to waste my time on that. It turns out, however, apparently, because someone tried to enter this, I don't know, I can't say if they entered it correctly or not, but I know someone told me that they tried this and it didn't work. WebAssign didn't like this for some reason. I guess it didn't like that inverse tanh. Okay, so it turns out there is another way that you could have done this. And that way is what's called partial fractions. Okay, that's what we're going to actually talk about today. I'm going to teach you guys how to do something called partial fractions. That being said, once you learn partial fractions, avoiding trig sub altogether would actually be the better strategy. So how would you actually do it without trig sub? So remember at the end of Monday's lecture, we learned that if we had an odd factor of x elsewhere in our function, trig sub was technically speaking not necessary. So what we could have done here was multiply and divide by x. Then we could have done something like a u squared substitution. So you would end up with 2u du is equal to 2x dx. And so your u du is equal to x dx. And so what you would see is this guy, your, let me leave this x on that other side. What you'll notice from this guy is this part here is a u du. This part here would be your u. This part here would be your u squared minus 1. And so without having to go through an inverse trig sub, you'd actually end up, without having to go through a trig sub, you'd actually end right back here, where we got to after like a whole other trig sub thing, which now even after we get the answer, we have to do a back substitution, right? So really jumping into this with trig sub wasn't really the best strategy. I mean, at this point, you don't know many strategies, so it's probably the only thing. And of course, it shows up in a trig sub homework, so you're poised to do the trig sub. But really, after I've taught you all the integration techniques, thinking trig sub here would actually be, to me, a very inefficient way to attack this problem. I would avoid the trig sub altogether. It's not necessary. I can get to this integral here, the u squared over u squared minus 1, a lot easier. And I can do it in such a way where the back substitution isn't necessary. So it's much more efficient to actually avoid trig sub altogether, and you can get here. And once you can do here, once you get here, there are a couple options, right? So from here, you can go a couple ways. You can go the inverse tanh route, or you can do the partial fractions route. Now, to be fair, as I mentioned, the inverse hyperbolics and hyperbolics in general, it's not something that most people use all the time. So it might even be something that you might have forgotten the formula for inverse tanh, and I wouldn't really blame you for doing that. So the majority of people would actually approach this problem using partial fractions, right? So that would kind of be the go-to method here. You ask 100 people to do this integral, 95, 98 of them would actually do the partial fractions way. Like you'll have the odd 2 people who actually remember that the integral of 1 over 1 minus x squared is actually the inverse hyperbolic tangent. But most people would actually do this the partial fractions way. So that actually kind of leads into what I want to talk about today. I want to talk about a whole new topic, which is it 7.3? I forget the section. But the point is, partial fractions is what I'm going to teach you. So now I'm going to teach you how to do this integral, this guy right here. Let's say you're in a situation where you don't like working with hyperbolic trig functions, or you just literally forgot all the formulas that deal with inverse, with hyperbolic trig functions and their inverses. There are other options, okay? So the main option in this scenario would be something that we call partial fractions. Okay, so this is the real beginning of today's lecture. So it was just a very long segue to get into this, but I just thought I'd point out some scenarios where this guy would come up. You guys already have experience with a problem where this sort of thing would actually make a big difference. And chances are, if you do partial fractions on that problem, WebAssign is going to accept the answer, because even if you apply the trig sub first, which is completely unnecessary, partial fractions is how you'd finish it off. So now that we've already spoken about that problem, I actually have a very similar example to that problem. Coincidentally, where is it? Yeah, so someone like that guy showed up here, right? So coincidentally, I already had an example that looked like that. So after going through partial fractions, hopefully you guys can go back to that example and actually try the problem a different way. So let's actually jump back into this. So partial fractions, there's an alternative. Now, suppose at this point, just to motivate the example again, to motivate this strategy, suppose at this point, you wanted to actually compute the integral of 1 over x squared minus 5x plus 6. Okay, what are our options at this point? So looking directly at this, a substitution is not going to work. It's not a basic rule. Can't really simplify it to be a basic rule because you have a sum of terms in the denominator. So what option do you have? Well, if all you knew was the knowledge up to 7.3, there's pretty much one option, trig sub. What you can do is you could complete the square. And that would look something like x minus 5 over 2 all squared. If you square 5 over 2, you get 25 over 4. So now you have to figure out what do I need to add or subtract the 25 over 4 to get plus 6. And I think it's 1 over 4. Is that correct? 25 over 4 minus 1 over 4 is 24 over 4, which is 6. So yeah, I think that's right. Then you would do a trig sub. And what would be the right trig sub here?
Wouldn't x minus 5 halves equal 1/2 secant theta?
Right, 1/2 secant theta. And then you'd continue. But at this point, come on. Yuck, right? Trig sub, it's very intensive on its own. Now I'm gonna have to be doing trig sub with all these fractions all over the place. It's not gonna be a fun time, right? So as far as now, what you know now, this is how you'd attack this problem. So you could get this problem in the current homework, and this is how you'd attack the problem. However, there is a better way. Here's a better way. Can't write today. Suppose you notice this fact right here, right? Suppose you notice that 1 over x squared minus 5x plus 6 is actually the same as these two fractions added together. And in fact, that is true. If we added these fractions over here, if I do 1 over x minus 3 minus 1 over x minus 2, this times that, I would get x minus 2 minus x minus 3 all over x minus 3 times x minus 2. When I simplify that, the x's cancel. I would get 1 over this guy. Right? So that's actually true. Let's say somehow you were to notice that for whatever reason. Hey, that's actually the same as this guy. It turns out that the integral on the left, this guy is much easier. In fact, now if I were to call this I, could you tell me what I is equal to, knowing that it's the integral on the right? It's now something you can literally do in your head.
ln of x minus 3 minus ln of x minus 2.
Fix that up a little bit.
It would be ln of x minus 3 over x minus 2, wouldn't it?
No, that's actually the same thing. We're off by a technicality.
Absolute values.
Absolute
values.
Plus c.
Right, plus c. So a couple technicalities, right? So if I were to notice that fact, right? The fact that that big fraction actually broke up into those smaller fractions, then the problem is actually easy. I don't need a whole trig integral and then I have to do a bunch of back substitutions and stuff like that, like bend over backwards, right? Compare that to, imagine that versus actually going through this problem, right? Obviously, if I were to notice this, this would be preferable than something like a trig sub, right? So that's what's called partial fractions, right? when we actually take a big fraction and we break it up into a sum of smaller fractions, these guys are called partial fractions. So if I have 1 over x squared minus 5x plus 6, and I break it up into this guy, these guys over here, these are called the partial fractions of 1 over the right-hand side. Right? And this process going from this to that, this is called the partial fraction decomposition. Right? So I can say, I can find the partial fraction decomposition of this big, large fraction on the left, and that leads to the partial fractions on the right. The partial fractions are just a bunch of smaller fractions that are obviously more easily managed, that actually sum up to the big fraction on the left, which means there's no difference between the two. Whatever I can do on the right side, I can do on the left side, right? So if I wanted to integrate the left side, it's the same as integrating the right side, right? Whatever I wanted to do, both sides will always give me the same outputs whenever they're defined, right? So this is the idea of the partial fraction decomp. Now, of course, no one's going to know, like in their head, just looking at some random fraction, what the partial fraction decomposition is, right? So if I have a major fraction, how do I even know that there exists such a decomposition? And how would I find it if it does exist? So that's the meat and potatoes of today's lecture. I'm actually going to teach you how to do this. How do you go from a big fraction to a bunch of smaller fractions? Okay. And we're going to, of course, apply this to making integrals easier, because sometimes I can have a big messy fraction and I don't want to have to go through something like a trig sub to get it done. I would much rather deal with a lot of smaller fractions, and I can then find the answer in my head, right? So that leads us to what's called partial fractions decomposition. And I'm going to actually teach you how to actually do this, how to break things down in this way, right? So how do you actually go about doing this? Well, of course, you have to start with a rational function, right? So this is a ratio of polynomials. And you have to start with a proper rational function, okay? So a proper rational function just means the highest power on the numerator is smaller than the highest power on the denominator. If the numerator has a power greater than or equal to the power of the denominator, this process is not going to work. You'd have to kind of clean it up a bit before. Another way to know that this thing can work is if the denominator factors. So if I'm looking at something like this, 1 over x squared minus 5x plus 6. One thing that I would immediately try to look for is, does the denominator actually factor? You'll notice that the denominator here actually factors into x minus 3 times x minus 2. If the denominator did not factor, then it turns out partial fractions would not work, and then I'm stuck doing something like a trig sub, because I'd always be able to complete the square. I can complete the square for any quadratic. I can't factor any quadratic over the rationals. So as long as you can factor the denominator and the numerator has degree smaller than the denominator, this process, the way of breaking down a large fraction into smaller fractions, this can work. So there are just some preliminaries that you need to check before you actually know that this will work. That being said, this is going to be the method here. So I'll pause here for a second so you guys can take a snapshot, because you'll probably be referring to these for examples later. However, I'm going to explain in detail each of these steps. How would you go through each of these steps? And then we're going to put it all together to solve some problems, right? So this is the method of partial fractions decomposition. So first of all, you want to make sure that the rational function you're looking at is proper. If not, you should make it proper. How do you make something proper if it's not? Well, I'm going to talk about that. Then the next thing is you're going to factor the denominator. You have to make sure that the denominator is factorable, and you're going to factor it fully, right? So that leads to the things you want to check. Do I have a proper rational function? Step 0. Step 1, is the denominator factorable? If yes, awesome. Partial fractions can probably work. It can work. But then you need to go through the process. So step 2, you're going to actually factor the denominator. Step 3, you're actually going to now break up the fraction based on the factors in the denominator. And I'm going to show you how to do this. Step 3 is to actually kind of modify step 3 part A based on certain situations. Like if you have a repeated factor, you have to deal with that very specially. Step 4 is you're not going to know the exact form of the numerator right off the bat. So you might have to do some process of solving for the numerator. And then 4B is actually a modification on step 4 as well. But once you go through this 4-step process, you'll actually have found the partial fractions. Now I'm going to go through, like I said, each step here individually so you understand, okay? All right, so let's expand on this. This is actually step 0. Okay, make sure that it is in proper form. What does proper mean? Like I said, proper means, and I think I typed that in the notes somewhere. Yeah, proper means the degree better. So I did type that up. So proper means the numerator has a smaller than degree than the denominator. If you look at this fraction, for example, x squared plus 1 over x squared plus 2, the degree of the numerator equals 2, right? Remember, the degree is the highest power. The degree of the denominator is also 2, right? So this means it's not proper. That is an issue. Okay, so let's say you see a fraction that's not proper, but you want to apply partial fractions. You have to make it proper. How can you make it proper? There are a couple ways. One, you can use algebraic manipulation, or 2, you can use polynomial long division. And I'm going to show you both of those on this example. So algebraic manipulation is when you do something like I did. Oh, there's a question here in the chat. Oh, well, I'm about to answer that question. Okay, so algebraic manipulation is what I showed you guys in the very first thing I looked at. When I did that thing where I added and subtracted 1 in a convenient way, or you can multiply and divide by something in a convenient way. So you kind of finagle things algebraically. So what would that mean in this situation? What I could do, for example, is I can add and subtract a 2. Okay, so now you might say, well, why would you add and subtract a 2? The point is to get the denominator in the numerator. You'll see why that is the point pretty soon. So my denominator looks like x squared plus 2. I want to get that expression, x squared plus 2, in the numerator. How can I get an x squared plus 2? I don't have an x squared plus 2. I have an x squared plus 1. Well, add the 2. But I can't add the 2. That's going to change the value. That's fine. Subtract the 2 again, right? So I add and subtract the 2 so that I get that, x squared plus 2. Now you notice that this part here is the same thing as the denominator. This now would look like the following: x squared plus 2 minus 1 over x squared plus 2. What you can do now is you can split the fraction. So I can actually split it here and then split it here. This guy would now become, well, x squared plus 2 over x squared plus 2 minus 1 over x squared plus 2. So now you see why I had the sign in the other one the way it is, to answer the question in the chat. And this now here, that just simplifies into that. And now what you'll notice about this guy, he's proper. right? The degree of the numerator is 0, while the degree of the denominator is 2. So I just went from a situation where I did not have a proper fraction, and now I have a proper fraction. One way to get this done is algebraic manipulation. Find out a way to add and subtract something, or multiply and divide something, or just to get the denominator in the numerator. Then you're going to split the fraction across the numerator. And then one part is going to simplify because you have the denominator is going to cancel. And then the part that's left over is going to be proper. So that's one way you can do this. So you can actually break this up into its partial fractions right there. So this means that if you have x squared plus 1 over x squared plus 2, this is actually the same as 1 minus 1 over x squared plus 2. Those two are the same. And at this point, it's already in partial fraction form. So this is algebraic manipulation. So this was an illustration of the first thing. Any questions on this? Are we good? See what I did and why I did it? Okay, awesome.
Professor,
Yes.
is there any other way, like, you know how you're saying in the explanation that you could do like multiplication and division too?
Yes.
Would there be a way to do that for this question?
Not that I can see.
Okay. Like you wouldn't multiply and divide by the denominator? That wouldn't be helpful here.
I don't see how that would be helpful, because then you're making your denominator larger, and then in the numerator you'd expand a bunch of stuff. It seems like it would make things more complicated.
Okay.
To me, yeah, we want to keep things simple. So the simplest way you can think about to get the denominator and the numerator is what you want. Adding and subtracting something is much simpler than multiplying and dividing by a quadratic. Here's another option, polynomial long division. You guys might have forgotten how to do this, and I'm not going to reteach you, but I'll actually just go through an example so you can actually see. So polynomial long division. Or synthetic division, but polynomial long division is better. It works in situations where synthetic division doesn't. So let's say I have x squared plus 1 over x squared plus 2. This is the same as saying, well, I have my x squared plus 1, and I want to divide it by x squared plus 2. And so now I actually go through and I do the long division. Now remember, when you're setting up the long division, you need to have a placeholder for each term. So even there's no x term, I leave a space for it because things have to line up correctly. So how does the long division work? Well, you take the first guy, so you take the x squared and you divide into the x squared. The result is going to be 1. You're going to take that 1 and you're going to multiply the guys here. And you're going to write the response underneath, lining everyone up. So it's 1 times x squared is x squared. 1 times the 2 is going to give me a plus 2. And then I'm going to subtract that from the above. You'll notice that the x squares now die. And I would have the plus 1 minus 2. So I would have minus 1. And that guy is going to be the remainder. And so this means that x squared plus 1 over x squared plus 2 is actually 1, namely this one up here. Minus 1 over x squared plus 2, where this one here is that one there. So you can actually do polynomial long division as well, right? So where this is coming from, it's pretty much like regular long division. So another example, let's say I had 27 divided by 2. You could have 2 into 27. Remember how we did that? 2 into 2 goes 1 time. 1 times 2 is 2. Subtract that, you get 0. Move the 7 down. 2 into 7 goes 3 times. 3 times 2 is 6. Subtract that, you have remainder 1. 2 into 1 you can't, so that's your remainder. And so then you end up with 27 over 2 is 13, which is the guy that's on top, plus the remainder over the divisor, right? So it's just that, but with polynomials. Okay. So actually make some space here for the other examples. Okay, so you can do polynomial long division. So let's look at a couple more examples. Let's look at this one. Here I have x cubed plus x. So remember, if I try to do version 1, algebraic manipulation, what I can do is I can factor off an x. Then I can do that trick I told you about earlier in the numerator. So I can add 2 and subtract 2. So that would give me x times x squared plus 2 over x squared plus 2 minus 1 over x squared plus 2. And so that actually simplifies to 1. And now I can multiply the x back out. So this is x minus x over x squared plus 2. And you'll notice that this second fraction here is proper. I could do this with long division. If I see x cubed, what did I put, plus x over x squared plus 2. What I could do is, okay, so I have x cubed, leave the space for the x squared, leave the space for the x. No, I don't have to leave space for the x. There's actually an x there. Plus x, leave a space for the constant. And I want to actually divide x squared plus 2 into that. So then I take x squared into the x cubed. I get x, take the x, multiply this entire side here. So I'm going to take the x, multiply this entire side here. I would get x cubed plus 2x. So I line that up here with the x column. Subtract the x cubes die. I would have x minus 2x, so I get minus x left over. And x squared does not go into x, so this here is my remainder. And so I get that my x cubed plus x all over x squared plus 2 is the x in the numerator minus the remainder over the divisor. All right, so I can get that as well. Okay, never mind. So I actually did both of those.
Professor?
Delete. Yes.
Is it just a matter of preference of whether we do
Yes.
algebraic manipulation or long division?
Yes. Matter of preference.
Okay.
There are times when something can be sufficiently complicated where you won't see the algebraic manipulation very well. And so you can think of the long division as kind of the brain dead way of doing it. Like if you don't see like a nice little manipulation, just do it the long division way, right? So you can think of it kind of like back in pre-calc, the AC method versus factoring something by trial and error, right? If you kind of see the numbers that would work right, you just do it. If you don't, there's a whole step-by-step process to go through to get to the answer, which we call the AC method. So that's how you want to think of the long division here. It's the thing that you would use if you don't see what to do, right? So maybe someone could look at this example, the x cubed plus x over x squared plus 2, and they won't see that factoring off the x was the right thing to do. And they're like, well, how can I get the x squared plus 2 in there? So if you didn't see that, then just do the long division, right? You'll get the same answer either way.
Professor?
Yes.
When you, after the, like, this is just a double check, but after this step, like when you integrate it, the x over x squared, oh no, sorry, the 1 over x squared plus 2 would be ln absolute value x squared plus 2, right?
No.
Oh, okay.
How would you do the 1 over x squared plus 2?
As of now, wouldn't that be trig substitution?
Sure. I mean, there's a nicer way. If I had the integral of 1 over x squared plus 2, I'd probably factor off factor out the 2. So this would be, say, 1 over x over radical 2 squared plus 1. And a u equals x over radical 2. My du would be 1 over radical 2 dx. And so this guy would end up being radical 2 over 2 times 1 over u squared plus 1. And so this would be radical 2 over 2 tan inverse. It'll be quicker than a trig sub.
What if we just did u equals x squared plus 2? Would that work out to the same answer?
Your du would be a 2x dx. Where would you get the x dx from?
Oh, yeah,
Right? I mean, the u sub would work if there was an x here. And then, yes, you'd get an ln from that, because you'd say u is the entire denominator. Your numerator would give you the dx. And then so you'd end up integrating 1 over u. But without the x in the numerator, it's not going to be an ln.
Okay.
Right, so that's how I would do that one. Okay. But the integration isn't the main point at this point. I'm just showing you how to actually break things down. Okay, let's keep going. All right, so once, geez, I hope nothing. Let me leave it. I'll worry about that later. Fix the formatting later. Okay, so once you know everything is proper, the next step is to factor the denominator completely. Now, I'm not going to teach you how to factor, right? We don't have time for that. So I'm going to assume everyone here knows how to factor stuff. By the way, if you've forgotten any of this stuff that I'm talking about now, like the long division and factoring and all that stuff, you can watch my Math 1000 lectures. That's when I taught pre-calc. It's also on YouTube. You can go over that and you can get that stuff. So all that stuff is there. I'm already spending more time on the elementary stuff than I want to. So let's keep going. Okay, so factor the denominator completely would be step 2. So let's assume that you have done that, right? And this involves you using sophisticated techniques like the rational roots theorem if it calls for it, right? But let's suppose that you actually get to a point where you can factor it, right? As far as I'm concerned, that step is self-explanatory. Then we move to the third step. So here is where things start to, what you really need to know about partial fractions. This is where it starts, right? So you have a proper fraction, you factored the denominator. So you could look like any one of these 3 examples right here. The next thing you want to do is you want to break up the big fraction into smaller fractions. And how you're going to break it up is based on the factors in the denominator. So let's look at the first example, 5 over x times x plus 2. The factors in the denominator are x and x plus 2. So you are literally going to break this up into a fraction where the denominator is x and another fraction where the denominator is x plus 2. You break up the big fraction across the factors of the denominator, right? because the LCD is going to be the product of the denominator. So this is how we're going to build back up to the original problem. Okay, now, an important part is how you fill in the numerator. Because off the top of your head, you're not going to know what are the right numbers to put in the numerator. So for now, you're going to put in some generic variables that would represent constants, but they're placeholders. It's very important that you fill in the numerator correctly. How you'd fill it in is what's highlighted here. Your numerator should be a generic polynomial. That is, let's actually change this. Let's make that red, because that's actually super important. 1 degree less than the base factor in the denominator. So here the base factors are the x and the x plus 2. These are both first degree polynomials. The highest power is 1, which means the numerators need to be 1 degree less. In other words, the numerators for the fractions in this particular example need to be 0 degree polynomials. What is a 0 degree polynomial? Well, it's a constant. So customarily, we just use uppercase letters to represent these constants. So I can put an A over this guy and a B over that guy, right? And that is the third step in the partial fractions thing. Just break up the things and put these generic numerators in. So let me show you how to do this second example here. So let's say, okay, I got 2 over x cubed plus x. I realized, okay, I want to do partial fractions. So I factored the denominator. So now it's 2 over x times x squared plus 1, which means this guy is going to break up into something over x and something over x squared plus 1, right? So the base factors here are the x and the x squared plus 1. So that's what I break up my fractions in terms of. Now, in the numerator, what I do is I put a generic polynomial that is 1 degree less. Exactly, it has to be 1 degree less than what's in the denominator. So for the first fraction, the denominator is a first degree polynomial, which means the numerator needs to be a 0 degree polynomial. For the second fraction, the denominator is a second degree polynomial, which means the numerator needs to be a first degree polynomial. How would that look if it's a first degree polynomial?
Bx.
As general as possible. What's the general form of a first degree polynomial?
X.
That's not general. That's a very specific one. What's the equation of a line?
Y equals mx plus b.
Right. So what does the right side look like? A constant times x plus a constant, right?
Mm-hmm.
That is a general generic first degree polynomial. You have to account for all powers counting down, right? X is a very specific one. X is the one where b equals 1 and c equals 0. But you could also have 2x plus 5, right? Your b is 2 and your c is 5, right? So the denominator was a second degree polynomial, which means my numerator needs to be a first degree polynomial. Okay. Someone tell me how you'd break this one up.
So it's ax, or a over x, plus bx squared plus cx plus d over x cubed plus 7.
Yes, exactly. So are we getting it now? How you actually break these guys up? So you factor the denominator, you split it into smaller fractions based on the factors of the denominator. The numerator needs to be 1 degree less than the base factor in the denominator. Now there is a slight nuance to this part, right? So it's very important that you realize that I just mentioned it's the base factor in the denominator. So it can be tweaked a little bit. For example, look at these examples here. And I'm going to, I guess, explain why after this. Okay, let's look at this first example, right? And it's very comparable to the first one here, except you will notice that the x plus 1 itself is squared, which means there is a base factor of x plus 1, but it's repeated, right? So there is a factor of x plus 1 in the denominator, but its multiplicity is 2. The important thing for you is actually the base factor. So the x plus 1 is the important thing. So that's very important. So here are the base factors. So I'm not counting their powers or anything. It's x and x plus 1, right? This is how we choose the numerator. Numerator chosen based on these. Okay, so that's the first thing you need to remember. So this is the same as the last step. However, there is a little bit of nuance on how you're going to break these guys up. Whenever you have a repeated factor, like something that has multiplicity of greater than 1, what you do is you have to further break that factor down into its base factors, counting up to the multiplicity. What do I mean by counting up to the multiplicity? Well, I mean, you would start one fraction with x, another fraction with x plus 1, and then another fraction with x plus 1 squared, right? If I had x plus 1 to the 5th, I would have a fraction with x plus 1, x plus 1 squared, x plus 1 cubed, x plus 1 to the 4th, x plus 1 to the 5th. I break down the base factors into all multiplicities counting up to the highest one that's present, okay? Now I'd fill in the numerators the same way. The numerators are filled in based on the base factors. So the base factor is x, which is a first degree polynomial. So this is a 0 degree numerator. For the second one, it is a first degree polynomial. This is a 0 degree numerator. For the third one, the base factor is a linear. It's a first degree. So I still have a 0 degree up here. So in the last one, I do not put a cx plus d. It's only the c. Why? Because it's based on the factor, the guy that's inside the parentheses. Okay, to make sure we understand that, maybe someone can tell me how you deal with this scenario.
So that one would be a over x plus b over x plus 1 plus c over x plus 1 squared, and then plus d over x plus 1 cubed.
Yes, right? So you see you're basing the numerator on the inner factor of the denominator, the thing that's in parentheses. Okay? Okay. So it's still, you're still following the 1 degree less rule, but that 1 degree less rule works on the base factor. It doesn't count the multiplicity. Okay, here's another one. Okay, maybe someone else can break this down.
So that'll be a over x plus b over x squared plus 1 plus c over x squared plus 1 squared, that whole set squared.
Okay, do we agree?
I don't agree.
How would you change it?
For the b over x squared plus 1, I'd put that as bx plus c over x squared plus 1, and then I'd make
right, because the base
last one.
factor here is quadratic. It has power 2, which means the generic polynomial that you put on top needs to have power 1. It's always 1 degree less, like always 1 degree less, right? That's why it's bold and underlined in red. It's always 1 degree less than the base factor. So with the base factor as a quadratic, the numerator has to be linear. If the base factor is linear, the numerator has to be a constant. If the base factor is a cubic, the numerator has to be a quadratic, etc. Right? Because if it's less, you might miss something. If it's more, it means it's not proper. You should have done long division first, right? You have to be exactly 1 degree less. This tells you that it's the most general thing that could not have been divided any further, right? So what would the third one look like?
Would it be dx squared plus ex plus f?
Okay, explain. Like for this last
think
one, what
it's
is the base factor?
Isn't it just dx?
Oh, yeah. I was thinking of cubed.
No, it's the
Would be-
same one. It's x squared plus 1 all squared.
Yeah. So it would just be dx plus e.
Right. Because you're focusing on the guy inside here, which is a quadratic. Now you might wonder, well, technically my denominator here is a 4th degree. Why wouldn't I put a 3rd degree, right? So that's a very common question that students would ask, right? Why is it that when I have a factor here that has multiplicity higher than 1, when I have a factor in the denominator that has multiplicity higher than 1, why does it break down in this particular way, right? Well, the idea is the following. If you have something like 1 over, say, x plus 1 cubed, the idea is we do break it down according to the rule that I said before. However, to make sure things can simplify, like where do you go with a fraction like this? To make sure things can simplify, you think of the base factor as the variable. So technically, yes, you would actually break this down into a quadratic. However, you think of the x plus 1 as the variable. So this would be x plus 1 squared plus x plus 1 plus c. Right? That is the most general thing you could think of. However, you kind of fix it so that the denominator plays well with the numerator. Kind of like how we did it with the algebraic manipulation earlier. Now, if you realize what happens here, if you start to break these guys apart, you start to realize that in the first scenario, this whole thing cancels 2 of those. This one would cancel 1 of those. And in the last part, nothing cancels. So you end up with a over x plus 1 plus b over x plus 1 squared plus c over x plus 1 cubed. So that's why it breaks up. So technically, we do follow the rule that I gave you in 3a, but we modify things in such a way that the variable is now the base factor. So even when I break it up in a way that gives me 1 degree less, it turns out for repeated factors, the breakdown looks like this. It's always based on the inner guy, right? So once you have a repeated factor in the denominator, you count up to the multiplicity and you make the numerators based on the base factor. So if I were to find the partial fractions of this guy, it would break down into 3 smaller fractions that look like this guy. And of course, if the point was to integrate or something like that, I'd rather worry about integrating this side than integrating that other side. But we'll get there later. Okay. Now, here's the part that you have to finish up. Because at this point, you don't know what the numerators are. Right? So eventually, usually you want to find the A, B, and C. What are the A, B's, and C's that I need to pick that would give me this original value? How can I choose the A, B, and C such that when I combine these 3 fractions, it actually gives me a 1 on the numerator, right? How can I make sure that happens, right? So that brings us to step 4 of this process. And basically step 4, there are 2 main ways that you can go about this. And then there's an additional trick that I'm going to teach you guys, right? So one main way is after you break things down, and I explain it in a paragraph here, so I'm just going to show you how this works. After you break things down in the way that I told you above, you're going to multiply both sides by the denominator on the left, and then you're going to plug in convenient values of x that allow you to solve for the coefficients. So what would that actually look like? So let's say I start off with x squared minus 5x plus 6. That is, of course, equal to, I can factor the denominator. So now I have this version here. Now I start the partial fractions. I would break this up into a over x minus 3 plus b over x minus 2. Okay, now what I can do is multiply both sides by the denominator on the left. So I multiply both sides by x minus 3 times x minus 2. So the left side now gives me 1. The right side would give me that. Right? So what I just did was multiplied both sides by x minus 3, x minus 2, the left denominator. Okay, now once you do this, let me highlight the fact that I'm doing method 1 here. I can plug in convenient x values, right? So convenient x values just mean x values that are going to help me solve for the a and b. Can you think of any convenient x values here?
2 and 3.
2 and 3 are super convenient. Why? If I plug in x equals 2, then the a gets canceled because of the 0, and my b would be that. So this term gets canceled, and I can solve for the b. I would get 1 is equal to minus b, or in other words, my constant b must be a minus 1. If I plug in x equals 3, then the equation becomes x times 3 minus 2 plus b times 0. So now the b gets canceled, and I can solve for the a. So now I can go back. What was the original? 5x plus 6. And I said, I know it's something over x minus 3 plus something over x minus 2. What's on top of the x minus 3? Well, that's a. A is on top of the x minus 3. And I just found, someone got kicked out of the room just now. Let them back in. My a is the number over the x minus 3, and I just found that my a is 1. I also found that my b is minus 1. And so this would give me 1 minus 1 over x plus 2, x minus 2. Now, if you go back to the very beginning of class, when I told you, hey, this guy breaks up into 1 over x minus 3 minus 1 over x minus 2, how did I know those were the numbers to pick? Here's how I know. Right? So I factored the denominator. I broke it up according to the rule that I mentioned. Then I multiplied both sides by the denominator on the left. I plugged in convenient x values to find the a and b, and voila, my a and my b must be plus and minus 1, respectively. So that's how I know that this guy is the partial fractions of 1 over x squared minus 5x plus 6. There's another method. Any questions on this method before we move on? Do you guys see what I did? Why I did it? So I started out with the equation that you see there under the blue writing. I cleared the denominators by multiplying by the LCD, which is always going to be the denominator on the left side. Then I plugged in convenient x values, right? Convenient basically means plug in x values that allows some of the variables to die, and I can solve for the remaining variables. there was another option that we could have done. So let's say I had that x minus 3, x minus 2. It starts out pretty much the same as the last method. I can multiply both sides by the denominator on the left. And what we do now is not plug in convenient x values. Sometimes there are no convenient x values. No matter what x you plug in, no one's going to die or get canceled. So another option would be to expand group-like terms. I don't know why this keeps doing that. So I group the x's, and then I group the constants. And then what I do now is something called equate the coefficients. Notice on the left side of my equation, I have 1, but I can think of it as 0x plus 1. While on the right side, I have a plus bx plus minus 2a minus 3b. Now, in order for this to be a true bona fide equation, the number of each kind of term that I have on both sides must be the same. They must balance out, which means the number of x's I have on the right must be equal to the number of x's that I have on the left. This tells me that my a plus b must be equal to 0. So I have that. This also tells me that the constant terms on the left must be equal to the constant terms on the right. So this part here must be equal to 1. So now I have a system of equations here that I can solve. Solve it using your favorite method, elimination, substitution, doesn't matter. But eventually you'll solve this and you'll get a equals 1, b equals minus 1. And so that gives you that your original fraction. Okay, so you could do something like in the first one, solve for a, you get a equals minus b, plug that into the denominator, you get 2b minus 3b equals 1, so you get minus b equals 1, b equals minus 1, then you go back, since your a is minus b and your b is minus 1, you get a is plus 1 and you can build it up. Or you can multiply the top equation by 2, then add the two equations, right? So again, algebra, if you need to review that part, how to solve simultaneous equations, Math 1000, I have the videos up. Right, so that's how you would go about doing that. So that's method 2. Any questions on method 2 or method 1?
I have a question.
Yes.
Is this also a matter of preference?
Indeed, yes.
Okay.
So you pick your favorite one. Personally, I like method 1 more. Personally, you can mix and match the methods. So there are times when you can plug in x values so that you can cancel everyone except one guy, but then any other x value you plug in, several guys will be there. Some people might like to switch methods at that point. So you can mix and match them. You can stick with one or the other. But eventually, if you can't think of x values that will do what this does and cancel out terms altogether, you can still obtain a system of equations from this. So for example, let's say I plugged in x values that weren't as convenient, like I plugged in x equals 1. Then I would get the equation 1 equals minus a plus minus 2b. That would be an equation. And I can plug in another x value, x equals 5. And I'd get another equation. Then I'd get a system of equations again. Right? So there are times, even when you don't have convenient values, you can still construct a system of equations using method 1. So yeah, this is a method 1 and method 2 matter of preference. And I did mention here, did I say that? Yeah, they can be mixed and matched. I mentioned that in the notes here. Right, but the main strategy behind method 1 is after you clear denominators, plug in convenient x values, hopefully you get some nice equations. If not, you can develop a system of equations that way. Method 2 follows the idea of expanding everybody, grouping like terms, and then setting coefficients equal to each other on both sides. You get a system of equations like that, and you can solve that. However, method 1 saves you from having to go through a system of equation in certain instances, for example, like in this instance. So I would have a slight preference towards method 1 unless I'm just in a situation where I can't actually cancel everyone except one term. Now, method 4, which is actually how to find the coefficients. There is a modification on this one that can actually come quite in handy. So this is, guys, called the cover-up method, right? So I'm going to show you this method. And the nice thing about this method is when it does work, it's actually quicker than both of the previous methods that I mentioned, right? So this is called the cover-up method. I'm going to show you why it's called the cover-up method. Okay, so let's say I have this guy. Right? And I break that down into a over x minus 3 plus b over x minus 2. Here's how you can figure out the things. And it's hard to describe like if I'm not there in person. So I'm going to do my best to actually draw this out diagrammatically at the moment. Cover up. That's why it's called the cover up method. Math people and naming things. Very creative. Cover up the denominator of a on the left. Okay, so if I see 1 over x minus 3 times x minus 2, the denominator of a is the x minus 3. I'm literally going to cover that up, right? So you can cover it up with your finger or whatever. Just ignore it, basically, right? Then what you're going to do is you're going to plug in the value that would make that denominator 0. i.e., plug in x equals 3, because then that would make x minus 3 equals 0. So you notice that if I took 1 over x minus 2 and I plugged in x equals 3, I would get 1 over 3 minus 2, which is 1. And that is what goes in the position of a. Now, I do the same thing for b. Cover up the denominator of b on the left. So on the left side, I see x minus 3 times x minus 2. I'm going to cover up the x minus 2 because that's in the denominator of the b. Plug in x equals 2, since this makes it 0. And so this would lead to 1 over x minus 3, where I plugged in x equals 2. And this is just going to be 1 over 2 minus 3, which is minus 1. And that guy goes in position B. And you're going to realize that this can make your life a lot quicker, a lot easier. So for example, here's another example, a very quick one.
I have a question really quickly.
Yes.
So when you say plug in the x value that would make the denominator 0, you're
Yes.
talking about
The part that you covered up.
The part that you covered up. Okay.
Yeah. That's why you have to cover it up. You're shunning away from division by 0. Like next time I'll explain to you why this actually works. But for now, that's the method. So here's another example. Let's say I have, 6 over x minus 1 times x plus 2 times x minus 2. I know that this is going to be broken up into x minus 1, x plus 2, x minus 2. When I'm looking what should go on top of the x minus 1, I would cover up the x minus 1, plug in x equals 1. I would get 6 divided by, so at that point, I would get 6 divided by 1 plus 2 times 1 minus 2. And that's going to be the numerator. When I want to know what would go on top of the x plus 2, I would cover that up over here and then plug in x equals minus 2. So the numerator here is going to be 6 over, I plug in minus 2, that's minus 2 minus 1, and plug in minus 2 here, that's minus 2 minus 2, and that's going to be what's on top there. Then to do this, I'm going to cover up x minus 2, and then I'm going to plug in x equals 2 into the remaining parts. So that'll be 2 minus 1 times 2 plus 2. So this actually breaks down into 6 divided by minus 3. And that's going to be 6 divided by 3 times 4. So that's what, a half? And in the last one, that's going to be 6 divided by 4, which is 3 halves. And those are actually the partial fractions. Which is, you might be thinking at this point, well, dude, that was super fast and I didn't have to do all this A, B's and multiplying across. Why didn't you just tell me this in the beginning? Well, the thing is, this method that I just showed you does not always work. There's a specific situation in which what I just showed you is going to work, and that is described in the notes here. It will work if you have non-repeating linear factors. It'll also work on the highest multiplicity of a linear factor, right? So if I did, for example, there was an earlier example that we had. So if I, for example, I could use the cover-up method here. The cover-up method would work to find the A. It would also work to find the C, but it could not work to find the B. And so that's why the other two methods are very important for you to know. The other two methods are far more general, but the cover-up method works in very specific situations. It works when you have linear factors and non-repeating linear factors. And it also works on the highest multiplicity of a linear factor. But that's called the cover-up method. So yeah. So at that point, we're pretty much wrapped up here. So I left some examples here for you guys to try. So I'd actually want you to do the partial fractions of these guys here. And then you're going to apply your knowledge of partial fractions to do these integrals here. Do as many as possible, okay? Now, obviously, once I gave you something like this, the integration of that should be something that you can handle, right? So I can give you this guy and ask you to integrate it, like, I don't know what to do. But then if you break it down to here, then yeah, now it's just a bunch of ln's, right? Being added together, right? It's minus 2 ln of absolute value x minus 1, plus a half ln of absolute value x plus 2, plus 3 halves ln of absolute value x minus 2 plus c, right? So you can actually just integrate very easily. So once you can actually do the partial fractions, and now you can go back to that original example I told you about, u squared over u squared minus 1. How would you do that without the inverse hyperbolic tangent? Well, this way. First, you reduce it into 1 minus 1 plus 1 over u squared minus 1. You'd factor the denominator, break it into its partial fractions, and you integrate each part. You'll get a u in the first situation, and you get 2 ln's. And then you can just back substitute the u. Yeah. So we're going to wrap up there. We'll do more examples next time, but you guys should, of course, try this because you have a quiz tomorrow. So for the quiz tomorrow, you should know how to break the simple kind of examples that I used here for partial fractions, and of course integrate afterwards. Yeah, that's it. Any questions on this stuff?
Nope.
Okay. So yeah, that's the cover-up method. It looks really neat. It doesn't always work, right? So that's why we couldn't just do that. But these methods above here, they always work. It's just that sometimes they can get tedious, especially if you have like a huge set of systems of equations to solve. It's a little bit annoying. However, if you remember your algebra, it shouldn't give you too much trouble. Yeah, cover method works in a few instances. I mentioned the instances here. I'll talk more next time about the cover-up method, why it works, and maybe show you a different scenario in which it can work where the higher power is. So let me actually just make a note of that. So note this, the cover-up method only works for non-repeating linear factors. Or the highest multiplicity of a linear factor. Only the highest. So if I had something like this, x plus 1 all squared, I broke that down into a over x plus b over x plus 1 plus c over x plus 1 squared. The cover-up method can find the a, it can also find the c, it cannot find the b. Okay. However, when it does work, it's actually a lot quicker than the other two methods combined. So again, it's another option. It's another thing that's out there that you can try.
Professor,
Yes.
even if it can't be used to find B in that problem, can it still be used to find A and C?
Yeah,
and then
and
you
then I
could
would
solve for
find
B.
B doing something else. Yeah.
Okay.
So again, all the methods that I just showed you, they can be mixed and matched. So personally, if I were looking at this problem, I would actually use the cover-up method for A and C. In fact, you can try it now on your screen. Cover up the x, plug in x equals 0. I know A is going to be 1, right? I can look at the problem and know A is going to be 1. What is C going to be?
-1.
-1, right? See, you just looked at it and told. Now the B, what I would do in that case is now I would plug in some random x value other than the x values that I just plugged in. And then I can just solve for B because I now know the A and the C. I can just solve for B by plugging in a random x value. I'd have an equation where there's only a B in it, right? So instead of setting up a system of 3 equations with 3 unknowns, I can do cover-up method for 2 of them, and then I only need 1 equation for the last variable. You see what I'm saying? So you can mix and match. So even if the cover-up method can't solve the whole problem, if you can use it on parts of the problem, it's still actually worth it.
Does it work for trigonometric functions?
No, partial fractions is a method of rational expressions. So if you're in a situation where you have a trig function that you want to do this with, you'd have to do some sort of substitution to make it not look like a trig function. Right, so like when we had the example earlier at the beginning of class, like let's say I asked you, yeah, let's say I gave you this integral. Partial fractions cannot work on that as is. However, after I do that substitution and I write it like this, now it can work. So it doesn't directly work with trig functions, no. It works for rational functions, ratio of polynomials. So partial fractions works for ratio of polynomials where the denominator factors and the fraction is proper. So you need those three things. It needs to be a ratio of polynomials, the denominator needs to be factorable, and the highest power in the denominator must be larger than the highest power in the numerator. If you don't have any of these, partial fractions won't work. Okay. So that was a lot, but I really went through each step individually. So we put it together for some examples in the end, but you might still be lost unless you actually try some problems. So try these guys for next time, and then also take a crack at these. Some of these might be pretty annoying to get through. I think B, C, and D was pretty, well, D is not that bad. I think B and C are kind of a little bit annoying. I mean, you can skip them if you want. I would at minimum, I would try A, try D, and then try these guys. Over the weekend, you can try B and C if you want. But if you want to kind of prep yourself for tomorrow, I would actually try those at least. Oh, hey, look at that guy. That was the guy we spoke about earlier. That was complete coincidence. I didn't, yeah. So I kind of already started that one for you guys. Yeah, so I suppose we can end there.
Thank you.
Okay, awesome. So I know somebody, I forgot it was who, wanted to meet with me during office hours. If that's still true, just send me an email and I'll send you the Zoom link. As for the rest of you, have a good night, take care, and I will see you in the next one. Ciao.